Welcome to my video course on engineering FRMCS. Today, we're taking an intensive look at the absolute heartbeat of the future railway mobile communication system, the mandatory Quality of Service Class Identifiers, or QCI, and their 5G equivalents, 5QI. You see, when we talk about engineering a highly reliable, congestion-free communication network for high-speed rail, what we're fundamentally talking about is prioritization. How exactly does the network decide what data moves instantly and what data has to wait? Well, the answer lies right here in these standardized QCI and 5QI levels. I am super thrilled to guide you through this critical matrix that makes modern railway communications possible, safe, and honestly, incredibly efficient.
Okay, let's dive right into this syllabus. First, we'll cover GBR for voice and video. Second, we'll look at delay-sensitive signaling. Third, core IMS signaling. And we'll wrap up with mission-critical data services. Before we start looking at the specific data tables, we really need to establish a vital foundational concept. In the world of 4G and 5G transport networks, traffic is broadly split into two main resource types, guaranteed bitrate or GBR and non-GBR. Think of GBR like a dedicated VIP lane on a highway. The network permanently reserves these resources so that continuous, delay-sensitive traffic can just flow without any interruption, no matter how congested the rest of the network gets. Non-GBR, on the other hand, is for traffic that can tolerate slight dynamic variations in bandwidth. It's still highly reliable, for sure, but it doesn't hold that strict permanent reservation of capacity. Keep this distinction in the back of your mind because it literally defines everything we're about to cover.
All right, Section 1, GBR, focusing on voice and video.
Now, what's really interesting about this slide is just how incredibly strict the requirements are for these specific values. Here we have QCI 65 and QCI 67, and these represent the only guaranteed bitrate values in our standard FRMCS framework today. QCI 65 is totally dedicated to mission-critical push-to-talk voice, or MCPTT. It demands a really aggressive priority level of 0.7 and a target latency of just 75 milliseconds. Right below it, we've got QCI 67, which is reserved for the mission-critical video plane. That one operates with a priority of 1.5 and a target latency of 100 milliseconds. Let's translate that raw data into physical reality for a second. 75 milliseconds sounds fast, right? But why is it mandatory for voice? Well, consider a high-speed train traveling at 300 kilometers per hour. At that speed, the train is physically moving over 80 meters every single second. So, in the tiny 75 milliseconds it takes for a mission-critical push-to-talk voice packet to traverse the network, that train has already moved more than 6 meters down the track. When a driver yells stop because there's an obstruction, this ultra-low latency for QCI 65 isn't just some abstract technical metric. It is a literal lifesaver. So let's contrast these two GBR values side by side. It might actually seem a bit counterintuitive at first glance. Video files are massive, right? They consume significantly more bandwidth than an audio stream. So why does voice, QCI 65, have a priority of 0.7, while video, QCI 67, gets a priority of 1.5? Remember, in this system, a lower number means a higher priority. The logic here is purely based on operational safety. In a crisis scenario where network resources might suddenly choke up, an urgent, immediate voice command absolutely must preempt high-definition visual feeds. The network is specifically engineered to drop frames of video long before it ever drops a single syllable of an emergency voice broadcast. Moving right along to Section 2, delay-sensitive signaling. Okay, I really want to draw your attention to this specific number, 0.5. Within the entire framework of 5QI and QCI levels we're studying today, 0.5 is the absolute highest priority level that exists on our matrix. Period. Nothing trumps 0.5. So the crucial point here is QCI 69. It's assigned to delay-sensitive mission-critical signaling. Look at the metrics here. It's a non-GBR resource type, which makes sense because it doesn't need a massive, constantly reserved pipe. Signaling packets are tiny. However, it commands the absolute lowest latency on the entire board, a mere 60 milliseconds, and it gets that ultimate highest priority of 0.5. So why does background signaling require such incredibly strict paramount rules? It all comes down to the protocol sequence. Before a train driver can even speak, the mission-critical system has to initiate the session. It has to coordinate floor control, which is basically determining mathematically who has the right to speak at that exact microsecond. If the network drops the session initiation packet, or if the call setup gets delayed while a fast-moving train crosses radio cell boundaries, then that 75 millisecond voice payload we just talked about, it never even gets transmitted. The signaling is the ignition. If it fails, the engine doesn't start.
And that is exactly why QCI 69 preempts absolutely everything else. Next up is Section 3, Core IMS Signaling. Here, we're examining QCI 5, which is dedicated to core IMS signaling. It operates with a priority level of 1 and a target latency of 100 milliseconds. Now, a priority of 1 is still incredibly high in the grand scheme of telecom networks. It's highly reliable and extremely fast. But in our specific railway ecosystem, it's distinctly subordinate to that 0.5 priority and 60 millisecond latency we just saw with QCI 69. To give you a bit of context, QCI-5 acts as the fundamental IP multimedia subsystem backbone. This is the baseline traffic keeping the network aware, handling standard device registrations, and maintaining those basic IP connections between the train and the trackside infrastructure. It's basically the steady pulse of the network. By assigning it a priority of 1, we ensure it functions flawlessly under normal conditions, but we explicitly guarantee that routine network management will never, ever preempt a driver's emergency radio command. And finally, Section 4, Mission-Critical Data Services. And this brilliantly illustrates the final piece of the puzzle. QCI values 6, 8, and 9 govern mission-critical data, or MCData. These are non-GBR resources, but look at the shift in the parameters here. The target latency is much looser at 200 milliseconds, and the priority drops significantly down to 5.5. So what actually travels on these 6, 8, and 9 levels? Well, this is where we find the data that makes modern automated railways efficient. We're talking about automatic train operation journey profiles downloading to the train, routine equipment status reports, non-urgent telemetry from the carriages, and just general rail operations support. Now, this data is absolutely essential for the railway business, but it's fundamentally different from a voice command. A journey profile packet can easily survive a 200 millisecond delay without causing a catastrophic event. By pushing this data to a priority of 5.5, the network can smoothly handle massive amounts of automated telemetry without ever risking the bandwidth needed for human safety. Pulling all the way back to the complete FRMCS quality of service matrix, you can see how it all fits together. In the event of extreme network congestion, this system operates with absolute, ruthless logic. It will instantly prioritize QCI 69 over everything else to ensure session connections actually survive. Once the session is established, it prioritizes QCI 65 at 0.7, so the emergency voice command is heard loud and clear. Then, it'll maintain the network backbone at priority 1, allow video through at priority 1.5, and finally process all that automated train data at priority 5.5. It's a perfectly orchestrated hierarchy that guarantees safety-critical operations never drop, regardless of the data load on the radio cell. Implementing these exact standards isn't just some nice-to-have best practice. It is the fundamental requirement for a highly reliable, interoperable future railway mobile communications system. By mastering this matrix, engineers guarantee the network can handle the immense complexity of modern rail operations smoothly and safely. But it really makes you wonder, as we push toward fully autonomous driverless trains in the future, will these specific latency standards hold up to the massive, unprecedented data demands of tomorrow? Thanks, we can see in next video.